In this video, we shall look at the open loop observable system, alright, in order to compare and design an observable controller. Okay, why is it open loop? Is because this is your input over here is going to go through all these things, alright, you also go through all these things, alright, and do you see any feedback? There's no feedback over here, and there's no feedback, there's nothing at all, alright, so therefore this is just simply an open loop system. Okay. And how can we use this open loop system to derive something that we can design for our controller and eventually to see the output of their dynamic systems? Alright, so how do we start? You can start first by determining the dynamics of your systems. Alright, this is your real system, your processes. Alright, and these are all the state space equations that you have once known, right? These are very familiar, AX plus BU. Okay, and this stuff's over here describes the states of the system, alright, and whatever thing that it is, alright. Taking note that this is Cx plus dut, but because d is always equals to 0, and therefore we will not go, and therefore is just plus 0, which is something like this, okay. And the reason behind why this d is equals to 0, I would suggest that you could watch l8v2 for the general for this state space system. We actually somewhat deal with you or somewhat show you the primitive way of solving for a state space system, where you can see that somewhat d eventually becomes equals to 0. Okay, I'll not go into details of that, but anyway, let's continue first. So we can model the processes, alright, the real system with this thing. How about we can model the estimated system? How can we somewhat see how the model works or the estimated system works? Is the same thing, alright. So the estimated, I'll just write as estimated model, alright. It's the same thing but slightly different. Okay, I'll just take in all the stuff over here, and instead of having the xt as xt's all over here, we'll have x hat dot x hat and y hat. Okay, well, this thing over here is also your boundary conditions. Okay, not boundary lah, for this one is your initial condition, sorry. Yeah, but anyway, what does all this means for this case? Okay, is that for your real processes over here, your x is your state for your xt over here. Okay, and therefore this is just the meaning, and your y over here is your y. Okay, for this case, your x over here is your x over here, which is x hat, as you can see, while your y over here is your y hat. So just simply subbing in all the y and the x hat based on their own stuffs, that's all. And the estimated system, alright, estimates the real model. The real model output its own things, it output its own things. Alright, while our model over here tries to model this system such that the error between them are somewhat very close to 0. Okay, and therefore how do we model the error? How do we see the error between them? Okay, one way is to look at the states, alright, where x bar is equals to x minus x hat. Okay, so this x bar over here is what we call the state estimated error. Okay, so your state estimated error is taking your state over here minus away the state over here, right? Because your input over here is going to go through your processes and going to go through this model also, that is going through the real and estimated system. Okay, so you have to compare the state, whether after you going through this system, will this state same as this state or not. Alright, but in a lot of cases, x bar over here, the difference between their states will often very hard to be 0. Okay, so that because x isn't just x itself, x can represent many states. You can represent x1, x2 all the way to x whatever. Alright, x hat can be represented by any x1 hat, x2 hat all the way to whatever x hat you want. Okay, so there is many states, so you cannot somewhat model so many state that is all the same. Alright, because if they are all the same, then this thing is equals to 0, because this one minus this one, if they are the same, then should be 0, right, the error between them. But however, in the realistic way, they don't. Alright, So we just take this definition first, and then we see how that we can model the system such that the error in some places can be 0. Then we can finally know that our estimated one is the same as the real one. Okay. As such, instead of looking at their state, alright, comparing their state, we look at to compare their dynamics. Alright, this is the error lah. Okay, error of dynamics. I don't know whether is this the name, but just to say that it's the error between your x dot t and your x hat dot t. Okay, your x dot t and your x hat dot t somewhat tells you the dynamics of your systems, right, after you interact with your input from u, which is at over here lah. Okay, but anyway, in such of the case, then what we can do is that instead of the x curly bar, alright, I'll have x curly bar dot, right, is equals to x dot t minus away x hat dot t. Okay, so if I take this one minus away this one, what I have is equals to this one. Okay, and then since we know that this thing over here is equals to this chunk, while this thing over here is equals to this thing, right, we have proved to you just now, right? I think you know what I mean, right? This one is equals to this one. If I were to bring this one to here, then if I just sub in this one, I think you get what I mean already. So what I'm gonna do next is just simply subbing in this stuff that I just told you. Alright? As such, what I have is this thing over here is equals to this thing. Okay? You can double check by thinking that you know that this thing is equals to this. Alright, and this is equals to this. Okay, just double check. Just simply subbing in only. Okay? And then this thing over here is equals to this thing over here. Alright, just simply subbing in this as this one. Okay, which is over here. You can just take a look, compare. Okay, just take a while to compare. Right, so as long as you don't feel that I'm cheated you, but anyway, yeah, you can write it down on the paper or whatever. As such, we can expand because these are unknown brackets. Alright, so I can expand this minus into the sides. Alright, because this thing over here is this one. Alright, they are plus. So these are all bracketed up together. So in order to expand this bracket, I need to multiply this minus into both of them. Okay, I hope that you get what I mean. So therefore, if I were to expand this minus into them, or what I will have is this thing. Okay, because I'm just simply multiplying it. Okay, and therefore, as you can see, your BUT and your BUT actually over here cancel out each other. Alright, and you may wonder why suddenly BUT minus BUT cancel each other, because from here your BUT and your BUT, alright, comes from where? Comes from this side. It shares the same input, right? So therefore this BUT and this BUT comes from this side, this one. Okay, and therefore if you were to minus away each other, you'll somewhat minus away their input, and you can only look at, and therefore then you can look at their difference between their states. Okay, I'm not going into details, but at least you get what I mean. Okay, so I just simply cancel out the BUT and the BUT. So what I have is AXT minus AX hat T. Alright, and this thing. And then since we know that we can factorize out this one, what I have is, because A is the common term, so I'll just simply factorize out. Now we have this thing over here. And if you take a look, this thing over here, alright, do you find it familiar? Okay, this thing over here is simply our state estimated error. Okay, as you can see, this thing over here. Or in other words, if I were to put this t over here, this thing over here is equals to this thing over here. Right? Take a look, take a second to just compare. As such, with this thing, then we can just simply rewrite your x curly bar dot is equals to x ax curly bar. Alright, so I'll just sub in this thing as this one over here. Okay, so far so good. And therefore, what does this mean? This is simply, if you remember back, this one over here is simply the difference between your dynamics. Alright, the systems, your system dynamics of your x dot t minus your x hat dot t. So it's just the difference between your processors and your estimator, alright, within their own system. Alright, their outputs and their output over here. So you're somewhat looking at their outputs. Alright, and therefore this is the differences between their output, so to speak. Alright, so to speak, I should say that it should be their dynamic responses. Alright, they are in terms of some graph lah. Okay, but anyway, we can sum up and come up with an equation, not equation but rather than we can assume that this thing becomes 0. Okay, why does this thing become 0? Is that when your error between your dynamic system of your processes and your real system and your modeled system is the same. So if your real system and your model system is the same, alright, and therefore the error between them, which is this is the error, alright, will eventually become 0. Okay, so when does this condition apply? Alright, when does this become 0? X curly bar or X tilde, alright, can never be 0 because we have proved to you, or we have somewhat not proved to you but rather informed you that these are all states. Alright, they are all states variables. X is x1, x2, x3 all the way. This one is x hat s1, x2 all the way. Or I should have write properly. X hat at 1, x2 hat, then x3 hat, x4 hat. There are many states all along. So therefore you cannot have all the states that are same as each other. Alright? But we can have the within their own systems, there are somewhat their responses between their errors to be 0. Okay? I don't know why it's within this that we want it to be 0 instead of this one. Alright, because this thing over here is also dependent of a lot of states. But anyway, I'll not go into that details because yeah. But anyway, since we know that this is equals to 0 and this will somewhat not equals to 0, the only way is to ensure that A multiplied by your x curly bar will be equals to 0 because A itself is a matrix. Okay, because your x curly bar is a lot of states. x1 minus x1 hat, x2 minus x2 hat, all the way to many things. So this whole thing over here is your x curly bar. Okay, so you're gonna multiply with your A such that you can find an eigenvalue. Then such that the eigenvalue, when you input into your functions, alright, you will have 0 over here. Alright, so when you have 0 over here, this means that the difference between your modeled system and your real system is 0. So your real system and your model system is the same. Okay, so in order to ensure that they are the same, we're going to use the eigenvalue of A. Okay, and if you were to solve for the eigenvalue of A by taking determinant of lambda I minus A equals to 0. Okay, if you don't do that, then eventually you can find your eigenvalue. So the eigenvalue, if your eigenvalue is equals to minus 0.1 or minus 0.3, your state response will somewhat be kind of very slow. Okay, slow. And this response over here tells you that your real system over at here is a slow output or something like that. It's a slow system. Same as your model, because if this thing is equals to 0, this means that the model system and the real system are the same. We have told you many times. So therefore this thing over here should be the same. And therefore we can see from our model system that the real system is somewhat very slow. Okay, the trend of the system is very slow. And if you have a eigenvalue that is pretty big, minus 100 and minus 300, alright, you have a very oscillatory system, very fast. Not oscillatory but yeah, oscillatory but eventually decay, but which is very fast. Okay, so we can see, so therefore we will know that your real system is a very oscillatory system, very unstable, and therefore you require somewhat a more robust controller to control your whatever processes that you want. Right? Therefore, when can you know that your system all over here is stable? Right? Is that your eigenvalue of your A alright, your matrix over here, and this one should be alright negative values, alright, which is why we have written all minus 0.1, minus 0.3, minus 100 and minus 300. Alright, it's because if it's negative, then this means that it is stable. Okay, this means that your system is in the left half plane. Whatever poles or zeros, whatever, your closed loop poles are all within this left half plane, which is stable lah, if you still remember. Alright, and if your error is, which is x curly bar is equals to 0, this is something I really don't know, because we have somewhat tell you that the error x curly bar somewhat it's very tough to be 0, right, which we have told you earlier. Alright, but if this is 0, your difference, your dynamic system should be also 0, and therefore the error between your normal, your real processes and your model processes is the same. Alright, and this raises the question of what is called stable. Is it stable because the response is stable, or stable means that your model is the same as your real system, then it's considered stable? Like, don't know what the hell, right? Yeah. But anyway, you just take it that in order to be stable, these are all the criteria that you want. Alright, minus v, etc. Eigenvalue of a is equals to this. Alright, and that the error between your responses, alright, for this thing over here should be equals to 0. In order to be 0, eigenvalue of a when multiplied with this curly bar, alright, should be 0. Otherwise, this x curly bar must be 0. Alright, which is shown over here. If such of the case that happens, then our modeling system is stable, so to speak. I don't know what the hell, but yeah. So I'll leave you to think about it for what is considered, what the meaning of stable is. Alright, but so far we have proved to you that we are able to actually model our system to such that the modeled system over here, alright, is the same as the real system. We have an equation to help us model the system such that your model estimator, whatever thing you observe, is equals to your real system. So with all the measurable states, alright, all the measurable states. If you still remember all the way back to our introductions, alright, we estimate the states from the available measurements. So if you have whatever measurements that we have, we just put it all over here and then we measure. Alright, these are the things. This is an open loop system, and later on in the next video we're going to talk about the closed loop system, where we'll first introduce you the problem of why open loop systems aren't very good. Alright, and later on we'll talk about it. So see you in the next video then.